All right, so in this section, I want to look at a few sort of simple sequences that whose limits we can't really find just using the limit theorems that we developed so far in this lecture. This is basically theorem 9.7 in the textbook. I'm going to probably only do the first two parts. I'm only going to prove the limits in the first two parts, but I do suggest that you look at it yourself. Maybe looking at the proof will be illuminating for you, the proofs of the other two, and definitely make sure that you familiarize yourself with all of the limits. But yeah, here, so let me just, let's just begin. So I'm gonna just state it. I'm gonna state the theorem part by part. So I'll state each part right before we prove it. So here we go. So theorem 9.7, part A. The first one that they handle is this. So they say limit a to the n. Oh, no, sorry. It's not this one. It's a limit of 1 over n to the p equals 0 for p greater than 0. Now, actually, we're only really going to be able to deal with rational values of p since we haven't really defined what it means for p to raise a number to a non-rational exponent. But the argument we use for rational exponents will be exactly the same as the argument you would use for any arbitrary real exponent after you define what it means to raise a number to a real power. Okay, so this is a very simple one. So let's just do a little bit of scratch. So hopefully you're getting used to this process by now. But basically, we want 1 over n to the p to be less than epsilon, right? So if you can actually just solve this for n, right? So this should mean that n needs to be greater than 1 over epsilon to the 1 over p power, okay? And again, right now this kind of only makes sense for rational powers, but this will make perfect sense if after you define what it means to take a real power. We won't actually be doing that in lecture, unfortunately. At least not that I'm not sure, but I don't think we will right now. Well, I don't know, it's pending. But anyway, so okay, so we have this right. So this is basically our n. So the proof would just be let epsilon be greater than 0. Then take capital N equals 1 over epsilon to the 1 over p for n greater than capital N. We have 1 over n to the p is less than epsilon. And there you go. Simple. Very simple. So that's that one. Now let's do the next part. And then I'm gonna go ahead and move on. I'll list the other ones and then we'll move on because I don't want to go through the proofs. I don't actually. They have some interesting tricks in them, but I'm not sure how generalizable those techniques are or anything. Even this one, the next one, I think is like maybe not super generalizable. It has some interesting stuff in it. I'll say that. So the next one is we're trying to show limit as n goes to infinity. Oh yeah, I mean, so you can include this n to infinity thing or not. I just did that out of reflex, honestly. They write it in the book sometimes and sometimes not. And I'm not actually sure exactly what governs when they put the n to infinity thing. But yeah, so the limit of a to the n should be 0 for absolute value of a less than 1. So this is obvious for a equals 0. So consider, or assume at least, oops. So let's assume 0 is less than absolute value of a less than 1. Okay, now the trick they use is, define b by A equals 1 over 1 plus B. Okay, so this might seem super weird at first. Like, why would you do that? First of all, or well, you might want to just mentally justify to yourself that this makes sense. You could actually solve this equation very easily for B and just by, or sorry, this should actually be absolute value of A. So B is positive. But yeah, you could actually solve this equation for B in terms of absolute value of A, and you'd find a perfectly perfectly good definition for B. I'm just going to write it like this for now. So A has to be like, because A is less than 1, right? It has to be of this form for some B greater than 0. And this is, so then what they do is basically, here's sort of the scratch work that went into this. So when you write A like this, then when you raise it to the nth power, then you can actually use the binomial expansion formula to expand the denominator. So this is 1 over, and then it's this big thing. So 1 plus n choose 1 b plus n choose 2 b squared plus so on plus n choose n minus 1 b to the n minus 1 plus b to the n. Okay. And then what they say is that, so because b is greater than 0, every term on the denominator here is actually greater than 0. So by deleting several of these terms, right, we'll be making the denominator smaller. And by making the denominator smaller, we make the overall value larger, right? So we can just actually, we can get an upper bound on a to the n by just like ignoring a bunch of the terms down here. So this is less than or equal to, it's actually strictly less than really, but it's enough to say that it's less than or equal to just 1 over n choose 1 times b. So we're only going to take, so we basically just ignore every other term. We only take n choose 1 b. Actually, let me do that in like red just to make it visually clear. In fact, so this one's good. Okay. So now, and n choose 1 is just n. So this is nb. So if we just make 1 over nb, so make, so we want to make 1 over nb be less than epsilon. That's the same as saying that we want n to be bigger than 1 over b epsilon. Okay? So basically this becomes our value of capital N. So yeah, it's tricky, but I think it's kind of interesting. It's definitely a very good example of just doing very rough, like extremely rough-handed estimation, right? That's what they do here. They just ignore like a million terms on the bottom of this fraction. And that's a very classic strategy in analysis, is just, you know, try to ignore stuff that you don't like. So as long as it doesn't hurt you to ignore it, then, you know, why not? So so the proof would be just take, well, okay. We forgot to let epsilon be greater than 0. I'm ignoring my own advice. Let epsilon be greater than 0. Take n equals 1 over b epsilon. Then the scratch. And when I say this, I really mean like if you're going to write this up all nice and stuff, you would actually insert the argument you're making over here where I write scratch, but I'm just not going to do that because I'm too lazy and it would take too long in the lecture. So the scratch implies, or sorry, the scratch shows, let's say, shows that when n is greater than n, then we have a to the n is less than epsilon. And that's all we want. That shows that a to the n approaches 0. Okay? So that's part B. And let me just now state the results for parts C and D without proof because it'll take too long for me to prove them. And then there's actually a question that I want to pose that I sort of meant to pose earlier and I was forgetting. So you'll get it now. Oh boy. Okay. Oops. Let me also. So the other two limits they state are the limit of n to the 1 over n is 1. Okay. That one might not be obvious just from looking at it. Although I would say that the thing that should sort of help you guess that this should approach 1 is that the function n increases much, much slower than any exponential function. So like if you took an exponential function like 3 to the n, like a to the n, but with a greater than 1, so like 2 to the n, 3 to the n, or like whatever, anything to the nth power, an exponential function, and you raise that to the 1 over n, you get a constant that's like bigger than 1, right? You just get the base of the exponential. But n is much slower than an exponential. So the 1 over n power just like dominates it completely. That's a good way of thinking about it, I think. And then the other one, or sorry, that was C. And then D was the limit of a to the 1 over n for a constant a equals 1. And that's like even more obvious. This is actually an easier one in a sense, but what they do is they do the hard one first and then they use that to easily prove the other one. So where a is a constant here, so a is greater than 0, right? That one's pretty obvious. But yeah, so these are other limits that it's good to be aware of. And like I said, you can't directly get these just from the limit theorems we've proved so far. But now that we know them, we can combine them with the limit theorems to get all sorts of like more complicated expressions, basically. Okay, so now I just want to pose, I'm going to end this section here by posing a question, very simple question. Yeah. So this will be lecture 4, question 1. So yeah, again, remember, this is a question that you want to submit on the homework, okay? Give an example of a sequence which is neither bounded above nor below, okay? A sequence which is unbounded in both directions. So pause, think about that for a sec, submit it on the homework. Okay, so hopefully you paused and thought about it. Now I'll just show you an example, okay? There's a very simple, so there are many, obviously there are many correct solutions to this. The simplest one I can think of is just Sn equals -1 to the n times n, right? So there are going to be a lot of questions kind of like this as we go forwards, as we introduce more and more properties of sequences like monotonicity and stuff like that. I'll be sort of like every once in a while, I'll ask you for examples of sequences that have a certain combination of properties or lack a certain other combination of properties or whatever that fit like certain criteria. And they can get kind of tricky. But the reason is that a lot of the time people have a very limited mental model of what sequences are capable of doing. So they'll assume that like one property will mean that the sequence can't have a different property when actually there do exist sequences which possess strange combinations of properties. So I'm trying to exercise your mind here and get you to sort of appreciate the full variety of behavior that sequences can exhibit. Okay, so that's the end of this part, and there'll be basically one more part where I talk about infinite limits.